Okay, this is Paul Geyer, and I will be the presenter today for this webinar, An Introduction to Fire Protection Engineering for Buildings. I want to place a little bit of emphasis on a couple of words in that title. The first one is introduction, because that's what this is. This is not targeted at engineers that have been dealing with fire protection systems in buildings for decades, and you're looking for a really nitty-gritty technical discussion. That's not what this is. This is targeted at all of the members of the building design team, and probably in some cases you only have a passing familiarity with the kinds of fire protection systems that are available and how they're applied and so on and so forth. So it's just an introductory course. Also, another word that I would want to place some emphasis on is buildings, because that's what I'll be talking about today. There can, of course, be situations where you are concerned with fire protection with other kinds of infrastructure features, but we're talking basically about buildings. A couple of housekeeping issues. The way the webinars move forward here with these webinars is I press on with the discussion for 50 minutes, then we take a 10-minute break, come back 50 minutes, 10 minutes, 50 minutes, 10 minutes. Now, this is just a 2 PDH or 2-hour webinar, so we'll just go through that cycle 2 times. Also, this is, of course, an interactive webinar. Questions and comments are welcome and encouraged. We've got 2 ways to communicate. One is you can just speak right up on the audio stream and I'll respond. The other is you can use the little chat box to type in a question or a comment. And occasionally there may be audio technical difficulties where we might be getting echoes and things like that. And if that happens, I may need to mute one or more of your audio streams to make that go away. In which case you would only have the chat box to communicate with. Right now, though, everything sounds fine. So my guess would be that we won't have to do any of that. Also, as indicated in some of the introductory material here, these PowerPoints that we'll be looking at today, you can get a copy of them if you want them for future interest, and you can get those from PDH Source from their website. Okay, that's it. Oh, one other thing on the audio business is remember that your microphone there at your computer or whatever you're using can pick up background noises there in your office, shuffling papers, taking calls, things like that. So be sure you are attentive to that and keep those kinds of noises out of the line. Okay, we'll be talking, of course, about fire protection, engineering fundamentals, materials and design. One thing that I spend a little bit of time on in these webinars is water supply, because this is something that sometimes we don't think about. We just think, well, fire protection water, I just hook up to the water line out in the street and that's the end of the issue. But that's not always the case. In some cases, you have to be concerned, does the water utility that's running out in the street there have enough capacity to deal with fire protection for your building? Um, and also buildings that are in remote areas, in state parks, et cetera, and there is no water utility out there. So we'll look at how you estimate the quantity of water that you need for fire protection purposes in your building. We'll talk a little bit about of course, about the fire extinguishing systems, how you put out a fire. The fire alarm systems, so what they are intended to do, and the kinds that are available. We'll talk a little bit about special occupancies and hazards. There are about a zillion special occupancies and hazards that are defined in the codes. I'll just touch on some of the more common ones, the ones that you're likely to run into in your building design. Um, and then storage of flammable and hazardous materials. Okay, and by way of introduction, this is a little bit about me and what I've been doing for the last few decades. For 35 years, I was what I characterize as a straight ahead designer, cranking out drawings and specs for the construction of buildings and a fairly broad spectrum of infrastructure features. I got registered in a few different things along the way, including as a fire protection engineer. I'm basically a mechanical engineer. That's my degree in my first registration. After that 35-year adventure, I then had an opportunity to do something that I had always had an interest in, which was in the public policy arena. And for an additional 9 years, I was a principal advisor to the California legislature on infrastructure and capital outlay issues. And occasionally there would be something about fire protection that would come up that some member or members wanted to know something about. So that's what I've been doing. These, for what it's worth, these are the learning objectives for the this webinar. And now these are the topics that I'll be touching on. One thing I need to tell you right up front, trust me, in 2 hours, I cannot tell you everything you would ever possibly want to know about fire protection engineering. It's a very large subject area. And a point to keep in mind is that it's almost totally code driven. There's very little that's of a theoretical nature. About the only time you'll be using any of your theoretical stuff is when you're doing hydraulic calculations for designing the piping system for water sprinkler systems in buildings. Other than that, you're constantly going to codes, and there are, well, not a million codes, but an awful lot of codes that have been produced dealing with fire protection in buildings. A large number of them, an extremely large number of them, are published by the National Fire Protection Association, NFPA, which is kind of the professional commercial focus for fire protection systems. It from just for historical interest, perhaps, the way NFPA got started, as I understand things, back in, I believe it was the early part of the 20th century, there was a very disastrous fire in a nightclub in a town in New England. It might have been Boston, or it might have been some outlying town. And there were a lot of fatalities, and the insurance industry actually took the lead in saying, well, wait a minute, we need to have some kind of codes or something to, to safely design buildings from a fire protection standpoint. So the insurance industry kind of took the lead. And as a result of their efforts, NFPA was created. And now, probably a little bit on the unfortunate side is, in addition to NFPA, the International Code Council is in the code writing business for fire protection purposes, and the ICC codes and the NFPA codes are not always consistent. But anyway, the codes, again, you are constantly going to these codes, these books, to tell you what to do in the design of your system for your building. And for those of you who might be interested in getting registered as a fire protection engineer, if your state recognizes fire protection engineering, and you take the exam, and it's I think in all of the states these days it's a national exam, and the key to success in taking that registration exam is to just make sure that you take a healthy number of codes into the exam with you, because that's what you're going to be doing is constantly referring to these codes. And the codes talk about the occupancy hazard classification of a building, what the building's made out of. Is it made out of wood, steel, concrete, etc.? And then the second point is, well, the occupancy of the building. What are the people doing in the building? Are they just sitting at desks in a quiet little office setting, or are they involved in some sort of a manufacturing or repair type process where there are hazardous things, liquids, kerosene, gasoline, etc., and the open flames like with welding being used. So what's the building made out of, and what are the people in the building doing? We'll talk a little bit about building materials and how they fit into the fire protection picture. Again, I said I'll spend some time chatting about water supply for fire protection, and where you, if you go through and do an estimate or a calculation of the water supply that you will need for fire protection purposes for your building, and you find out that you don't have that quantity of water available, either from the local water utility or maybe from some other source, well, then you're in the position of needing to store water on the site of your project for fire protection purposes. And a place where you can see this pretty frequently in the real world is in large warehouse types of developments, industrial parks, things like this. You'll drive around and adjacent to some of these big warehouse or commercial buildings, you'll see a structure that may not look exactly like a water storage tank, but may be architecturally incorporated into the design of the building. Well, that thing that you're looking at sitting beside the building is a water storage tank for fire protection purposes. And a reason, incidentally, that you see this in industrial parks, warehouse parks, things like that, is that warehouses are a particularly hazardous type of building from a fire protection standpoint. And you might think, well, that's a little odd, because a typical warehouse, you don't have a lot of people in it, and you don't have them doing much more than moving products around and shipping them out and things like that. But the reason they are a particularly hazardous type of building is because of all of that stuff that's stored in a warehouse is fuel for a fire. So that's why warehouses are particularly threatening, if you will, from a fire standpoint. The fire extinguishing systems, how do you put out a fire? The most common way of putting out a fire, of course, is with water. And that water often is delivered through an automatic, excuse me, an automatic fire sprinkler system. But it's also delivered through the hoses of the firemen when they show up to put the fire out. The fire alarm systems, and then we'll talk about a few of the special occupancies and hazards and those types of buildings or parts of buildings that require special attention. The building materials and design, these are some subtopics there, and we don't have time to go into them in any great detail. Water supply, when I start talking about that, I talk about water supply for a sprinklered building and for an unsprinklered building. A sprinklered building means it has an automatic water sprinkler system, and an unsprinklered building does not. And an unsprinklered building, basically what you have to rely on to put the fire out is the fire department. Okay, and then the fire extinguishing systems, the automatic water sprinkler system, of course, is the most common and very effective way of putting out fires, as long as the fuel is not something that's particularly hazardous, like kerosene, gasoline, etc., etc. Other types of ways of putting out a fire are dry chemical systems, CO2, carbon dioxide, and clean agent. Originally, they were typically a proprietary system, Halon 1301, but we'll talk more about that later. And then we'll talk briefly about the fire alarm systems. And basically what a fire alarm system does is it detects a fire, It reports a fire, like to the fire department, and it sounds an alarm, a local alarm, to tell people to get out of the building. Now, the special occupancies that you will probably from time to time have exposure to in run-of-the-mill buildings is food preparation areas. Kitchens are particularly hazardous because you're dealing with open flames and hazardous substances like grease and that sort of thing. Medical facilities like hospitals, the thrust with these types of facilities is that you are dealing with an impaired population. In other words, a fire breaks out, the alarm goes off, everybody runs out of the building. But the problem with the medical facilities, of course, is that some of the people are impaired and can't run out of the building. So you have a different strategy in those facilities. Detention facilities are the same thing. You've got an impaired occupancy, prisoners in cells. So if a fire breaks out, they can't run out of the building. And so you have to have a different strategy with them. And in some cases, it's somewhat similar to the strategy in medical facilities. Electronic and telecommunication facilities here, the challenge is that you've got a whole bunch of very expensive electronics and telecommunication system, and to try to put out a fire where it breaks out in the wastebasket. You don't want the automatic water sprinkler system overhead to come on and flood your and ruin your electronic equipment, as well as the data that you're processing and storing. So you have to use a different type of suppression systems there. And then high-rise buildings are also a challenge that we'll talk more about. As I said right at the start, keep in mind that fire protection business is almost completely driven by codes and regulations, and you are in every situation you're faced with in building design. You're inevitably going to have to be hunting around to get the right code and to look up the situation that you have and how you address it from a design standpoint. Another point to keep in mind if you're when you're preparing the drawings and specs for your building is that, of course, they all get reviewed by, at least in the civilian, the commercial sector, they get reviewed by the building department, the regulatory authority. And in your typical building department, the plan reviewers are engineers or well-trained engineering technicians. So they know what they're doing and they know what you do in the design of a building. But with fire protection systems, in addition to the building department reviewers, typically your drawings are going to be reviewed by the fire department. And here there's you need to use your diplomatic skills, if you will, because the plan reviewers in the fire department are typically just are typically firefighters who have had a little bit of training in plan review, but they really don't, they're really not up to speed on building design and that sort of thing. So the point is with your drawings and the fire protection systems is you need to take particular care to tell your story on the drawings and the specs and lay everything out so that the fire department reviewers can understand your thought processes, because they can stop your project dead in the water if they feel that they need to. Okay, now another point I want to emphasize is what we're talking about today is just an illustration of fire protection engineering. This is not a design manual. It's not a design guide. Any of the examples or points that I make here are for illustration purposes only. Okay, you've got a project that came in the front door and you've been assigned to design the fire protection systems for the building. Well, step number one really, and this is part of telling your story to the plan reviewers so that they can follow your thought process, is a design analysis, just as there is and should be a design analysis prepared for all of the features of a building: structural, mechanical, electrical, et cetera, et cetera, et cetera. So for the fire protection systems, this figure one here kind of gives you an outline of what you should address in the design analysis. And you can review this at your leisure. You note here there's a line on NFPA 101, which is the life safety code. There are kind of typically two codes that you're going to be dealing with. There's a fire code, but then there's life safety code. The distinction is that the life safety code is essentially concerned with getting people out of the building safely. So that's things like, corridors, construction systems that you use for the walls and the ceiling of the corridors. The corridors are very obviously very important, simply because in the event of a fire, everybody leaves their offices or wherever they are, and they tip in the typical building. They enter a corridor, and then they all exit the corridor into the outside, and then they're safe on the outside of the building. The point is that corridors need to have typically a greater fire resistive construction than other interior partitions in a building. A key point in fire protection engineering is to prevent the fire from spreading from where it breaks out to other parts of the building where it endangers people in other parts of the building. And also something that fire protection engineers have come to have a greater appreciation of in recent decades is that a lot of the threat, the hazard from fires, is not a result of flames as it is smoke. smoke is a big hazard. So this is a kind of an outline guide that you could use to prepare your design analysis. And this is what will help, in particular, the fire department reviewers to follow your thought processes. Now, occupancy hazard classification systems, of course, are designed by, are defined by codes, and the nomenclature varies every time they come out with a new edition of the various building codes, fire codes, and that sort of thing. The terminology that I'm using here may be a little out of date as far as some codes are concerned, but essentially you're classifying the buildings based on the what you are constructing the building out of: wood, steel, concrete, et cetera, and then what the people are doing inside the building. And these can range from light hazard occupancies, like a building that's built out of CMU block construction, not flammable. The people inside are just working at their desks, doing paperwork, that sort of thing. That would be a light hazard occupancy. And then the classifications get more severe, if you will, as you go down the line. The light hazard occupancies, those buildings that are least hazardous from a fire protection standpoint, and could be classified, or the terminology that might be used, as light hazard occupancies. So these would be places like offices, churches, gymnasiums, etc., child development centers. Getting a little more hazardous, the buildings types might involve kitchens and bakeries, restaurants with a kitchen in it, shops of one sort or another where flammable materials may be being used, and open flame may be present. Laundries, parking garages, of course, the hazard there is you've got all those automobiles sitting around with tanks full of gasoline, and that's hazardous. Theaters and auditoriums, the issue there is that you have large numbers of people in relatively small spaces. So if a fire breaks out, the issue is, how do you get all of those people out of the building safely? Getting a little more hazardous, ordinary hazard group 2 might be buildings that were uses were things like department stores, supermarkets, electrical shops, laboratories, switchgear rooms. The thing that makes these more hazardous in the cases like of department stores and supermarkets is the large quantities of fuel, that is, stuff that burns inside the building. And then the special occupancies are things like warehouses. Again, warehouses are particularly hazardous because they have such a high density of fuel, stuff that will burn in them typically. And then, of course, things like aircraft hangars, where you've got airplanes with a whole lot of fuel in them. The Okay, the building materials and the design of the building. A key point is that you want to prevent the fire from spreading from where it breaks out in the building to other parts of the building, because then you are jeopardizing other people in the building. And the way that you prevent the fire from spreading, first of all, is by having an automatic extinguishing system like water sprinklers that will automatically spray water on the fire. But then also from the barriers that you construct in the building, interior walls, ceiling, floor, this sort of thing, building those barriers out of more fire resistant materials prevents the fire from spreading as rapidly. And of course, from a life safety standpoint, egress, getting the people out of the building. Fire breaks out in one location in a building, alarm goes off, and a local evacuation alarm sounds. People have been instructed and trained to get out of the building expeditiously. That almost always involves moving into a corridor, and then everybody moves out of the building. Now, in the category of corridors, bear in mind that that also includes stairwells. A corridor, in the common way we use the term, is a horizontal exit path. A stairwell is a vertical exit path. And of course, we're all very familiar with those in multi-story buildings that we've been in. And a key point in fire protection engineering is that a person is somewhere in the building and a fire breaks out somewhere else. Like, as an example, a person is in the building, a fire breaks out on the left. Well, if the only egress route that that person has is to the left, he can't get out safely because the fire is blocking him. That's why in building design, you always want the occupants of the building, no matter where they are located within the building, to have two ways to get out of the building in the event of a fire. So fire breaks out on the left, occupant can't get out by going to the left, but he can get out by going to the right. So that's why in a simplistic picture of a typical building, you might have, we'll say, a corridor down the center. You have occupied spaces on the two sides of the corridor, and the corridor can exit to the left and to the right. And the also stairwells, typically, a typical multi-story building has a stairwell at each end of the building, the left and the right. So a person on one of the upper stories can get out of the building by the stairwell on the left or the stairwell on the right, go down, get out of the building. So that's an important point to keep in mind. Now, interior finishes are important in fire protection because of the issue of flammability and smoke generation. And some of the materials that have been used in building construction in the past were pretty flammable. Some of the insulations, this sort of thing, things like drapes hanging on the walls, perhaps as a decorative feature. They're flammable and they generate smoke. And again, the smoke, of course, is a big hazard to the occupants. Roof coverings, this is important, a concept to keep in mind, because what you might call the heat vector of a fire is straight up. That's just the way fires burn. The hottest part is pointed to the sky, and so the roof the building is particularly important that it have a high level of fire resistive construction because first of all, it's under the greatest heat stress probably, but also with roofs, a particular danger there is that in the event of a fire in a building, the fire breaks out of the roof. It can throw because of the thermal currents that are developed in a building particularly when the roof blows off and the fire blows out of the top of the building and blows out burning debris. The point here is that your building on fire is then putting nearby buildings at risk. This is kind of the Chicago fire illustration where the fire started in Mrs. O'Leary's barn and it just spread from building to building to building. And so to protect nearby buildings, the roof of the building needs to be constructed of a highly resistive system. And you have to, so that involves selection of the structural members of the roof structure, the covering materials for the roof, and then also typically you construct a parapet wall around the roof so that any burning debris that's blown out of the top of the building will be contained on the top of your building and not fly over to an adjacent building. And so these parapet roof requirements in the codes, they will be more stringent when your buildings are close together. Also, the closer together your buildings are, the greater the codes will require fire resistive construction. Again, that's kind of why you see if you have multi-story buildings, for instance, typically the walls that are adjacent to other buildings are of a highly fire resistive type of construction, like poured in place concrete, things like that. Another important point is fire department access. First of all, the fire department has to be able to get their fire trucks right up to your building if it's on fire. And this is one of the major things that fire departments will be looking at when they're reviewing your plans. Can we get our fire trucks right up to this building? The typical simplistic example of what the firefighters are doing is they drive up to the side of the building and they develop a pumper truck that has a pump in it. So they'll take a hose, run it from the fire hydrant in the street to their truck, and then it goes through the pump where the pressure is increased because the street pressure of the typical municipal water system will only get the water up to a limited number of stories vertically, 10 stories or something like that. So if you've got a 20 or 30 story building, you've got to increase the pressure of the water in order to get it to the top of the building. And typically within the stairwell, there will be a standpipe and that runs vertically the full height of the building. And at each floor on the building, there will be a tee-off that will connect typically to an automatic sprinkler system on each floor. And also there will be a connection point for firefighters to connect their hoses. So the firefighters pull up to the side of the building, connect a hose to the hydrant in the street, to the pumper truck, and then on the other side of the pump, they connect to this standpipe in the stairwell and pressurize the standpipe. And the firefighters then, because the stairwells have been constructed of a highly fire resistive nature, they climb up the stairs carrying their hoses until they get to the floor where the fire is. They connect their hoses and they go in and they fight the fire. Now, another important feature with multi-story buildings is what floor is the fire on? Well, systems have been developed so that in the event of a fire on an upper story, a signal, not only does a local alarm sound, not only is a signal sent to the local fire department, but a signal is also sent to a fire control panel, typically located on the first floor, either just outside the stairwell or within the stairwell. And the signal is sent to that panel and a red light comes on and says the fire is on the 13th floor. So then the firefighters know where the fire is and they don't have to waste time looking on every floor. So they pull up, connect the hose to the standpipe, look at the fire control panel. It says the fire is on the 13th floor. They carry their hoses up to the 13th floor. On the 13th floor, an automatic sprinkler system will have activated and is spraying water all over the place, and they connect their hoses and similarly start spraying water all over the place. So anyway, let's see now. I'm looking at my clock here, and there's a lot more information on this, these PowerPoints than we have time to get into by any stretch of the imagination today. And but you can review these at your leisure, and it will continue to flesh out this picture for you. Now, I talked about fire resistive construction of interior partitions. And a point to keep in mind is that if a barrier, a wall, is required by code to be of 2-hour fire resistive construction, everything in that wall has to be of 2-hour fire resistive construction. And that includes doors and windows. Now, how do you know who says what the fire resistive rating is of a certain type of wall construction? 2x6 steel studs at 16 on center with 5/8 gypboard both sides. What is the fire resistive construction and rating of that barrier? How is it determined? Well, it's determined by test, and it's determined typically by an independent testing laboratory like Underwriters Laboratories. And they just uh, construct a test using an ASTM methodology, appropriate ASTM methodology. They construct a test wall and subject it to a fire, and using the methodology, they decide that that construction should be rated as 1-hour fire resistive construction or 2-hour or whatever. And the same thing is done with doors and windows. The manufacturers hire Underwriters Laboratories to test them and give them a fire rating. Okay, we're here at 10 minutes before the hour, and we need to take our first break. So let's do that, and we'll come back on the hour and proceed. And then we'll, in the second part, we'll be talking about this frequently overlooked issue of the adequacy of the water supply for fire protection purposes. So I'll see you all in 10 minutes and we'll press on. Okay, this is Paul Geyer and I'm back. And let's press on here. Let's see, we need to kind of speed things up a little bit to try and get as much of this touched on as we can. Interior finishes, the key thing there is flammability and in particular smoke generation because of the hazard of the smoke. The roof construction, the roof coverings, and the roof deck assembly, how you put it together. These are all covered in the in these numerous codes, and so as a result, you specify a roof covering that has a high level of fire resistive construction. I was talking earlier about the firefighters when they pull up in their trucks and hook up their hoses and climb up the stairwell to the floor where the fire is has broken out, but also the firefighters are quite concerned about being able to expeditiously get to the roof of the structure, and that's so they can keep the roof from failing. And so they want to be able to keep the roof wet and prevent the fire from breaking out through the roof. Because of as I indicated, because of the hazard that poses then to nearby buildings. And vehicular access, again, this is one of the primary things that the fire department will be looking for is, can we get our truck up to the side of your building? And all the same applies, of course, to aerial apparatus, ladders, that sort of thing. Now, air handling units, this is an important point in fire protection, is, as I indicated, there has come to, in recent decades, to be more and more of an appreciation of the fact that in many cases, the most hazardous thing to the occupants of the building is the smoke, not the flames. And generally speaking, fire protection, the objective of fire protection is life safety. It's not really being done to prevent the building from burning down. The fire protection philosophy is that that's the insurance company's problem. When the building burns down, they just have to pay the owner and you can rebuild the building. But it's the life safety that's critical. And the air handling system in an air conditioning system in a building has become more and more a focus from a life safety standpoint, because flames can be transmitted through the air conditioning ducts, and most importantly, smoke very quickly can be sucked out of the location in the building where the fire breaks out and quickly distributed to other occupied spaces in the building. So it's the smoke is particularly hazardous, and it The the current state of the art, if you will, as far as air handling systems in buildings is that, from a fire protection standpoint, is that if a fire breaks out, typically you would want to immediately shut off the fan that is moving the air around the building through the ductwork system, so that the fan is not assisting to move the smoke from one area to another. And uh, this all depends on the configuration of the building and this sort of thing, but there another thing that tactic that can be used is through the duct configuration and the use of automatically actuated dampers, fire dampers, smoke dampers, to perhaps reroute, keep the fan that's pressurizing the HVAC system, keep it operating, but route the air from the space where the fire breaks out so that it is exhausted directly to the atmosphere. And so you're sucking the smoky air out of the building and exhausting it outside. Sometimes this may involve a second fan that does not come on except in the event of a fire. And so the main air handler fan shuts off, the automatic dampers reposition as appropriate, so that then this other fan, an exhaust fan, sucks the air out of the location where the fire broke out and exhausts it outside the building. Dampers also are inherently part of a contemporary HVAC system, because anytime, as an example, that an air conditioning duct passes through a barrier, a wall that is required to be of some level of fire resistive construction, 2 hours or whatever, the any duct, as an example, that passes through that barrier must also have a 2-hour fire resistive construction. And so you have fire dampers commonly used in air conditioning systems. Frequently they're activated by a fusible link that melts, and the fire damper drops down by gravity and shuts off the flow of air in the duct system at the fire rated barrier construction. Sometimes these, in this day and age, these are electronically actuated automatically. But the point is that anything like a duct that passes through a fire rated barrier also has to be fire rated, and these fire dampers are fire rated. Pretty much talked about the smoke and heat vents. Building materials, a point is that, as an example, in a common type of air conditioning system in a building, the supply ducts run to the occupied spaces, discharge air into them. And then the air pressure pushes the air out of the occupied space into the plenum space, which is the space between the floor deck above and the drop-down ceiling. And there is no return duct system, but a plenum, that space above the ceiling is the return duct to return the air back to the air handling fan. And so that is the return duct. And a point is that if you have a plenum system in a building, a plenum return system, you don't want to put any stuff in it that is flammable or develop smoke. So this would be things that you are plastic conduit with flammable or smoke generating insulation coverings, things like that. Okay, now let's move on and talk about water supply. Is there enough water available for my building for fire protection purposes? And again, this, in looking at the question of water supply, it kind of falls into two categories. The water supply for a building that has an automatic fire sprinkler system in it, in which case the amount of water that's needed is that which is needed for the automatic sprinkler system, and that quantity that is needed for the firefighters to use when they show up. The other category of buildings is unsprinkled buildings that do not have an automatic fire sprinkler system, and the quantity of water that is required is just that that is needed for the firefighters' hoses. So the two categories. Now, here is, let's get to this. Yeah, here is one system approach to determining the water requirement for a sprinklered building. Now, this approach that we're looking at now, this comes from a federal source, the Corps of Engineers and the Naval Facilities Engineering Command particularly, but there's nothing governmental or military or anything like that about this system. This is just good, solid engineering technical guidance. And we need to remember or keep in mind that the Army Corps of Engineers and the Naval Facilities Engineering Command are almost definitely the most experienced engineering and construction organizations in the country, perhaps in the world, in building design. So this is proven technical guidance, and it's pretty straightforward. So you've got your you've got a building that the code requires have an automatic fire sprinkler system in it, and increasingly the codes are requiring automatic fire sprinkler systems in more and more buildings. The ones that are still outside this requirement typically are residential buildings, particularly single family residences, but some other residential occupancies as well. So the code requires that this building have an automatic sprinkler system in it. And you have the occupancy classification shown in this table, ranging from the light hazard, and as you move down the table, the occupancy hazard rating increases. So the quantity of water in this system that is required for the automatic sprinkler system is that which is shown in the second and third columns from the left. The design density, gallons per minute per square foot of light hazard occupancy area, and the design area is 3,000 square feet. And you move down the table till you get to the extra hazard group 2. These are quite hazardous occupancies. And the design density that is required is greater. It's 0.4 gallons per minute per square foot. And the design area is 3,000 square feet. Now, at first glance, this may seem a little counterintuitive. Why is the design area for a light hazard occupancy 3,000 square feet, which is the same as the design area for an extra hazard group 2, the most hazardous type of an occupancy, also 3,000 square feet? That seems counterintuitive, but actually it isn't, because the thinking is, and this is perfectly logical, is that for the more hazardous occupancies, you'll put more water on the fire, a greater GPM per square foot. And by doing so, you limit the spread of the fire to this design area, 3,000 square feet. So that's the point, is that you're, in theory, if you have these quantities of water that you are applying to the fire, the fire will be limited to, let's see, Jeffrey says, plastic piping trend for domestic water supply, implication for firefighting. Well, you don't use, you would not use plastic pipe for a fire sprinkler riser, something like that, or for the piping for a sprinkler system, an automatic sprinkler system. I'm pretty sure, I don't sit here reading these codes every time they come out with a new edition, but I'm almost awfully positive that plastic piping would not be allowed for the water sprinkler system in a building. I don't know if that answered the question very well, but anyway, so light hazard occupancy, the design density 0.1, design area 3,000 square feet. So the GPM, gallons per minute of water required, would be 300 for the automatic sprinkler system. Then you also, though, have to have a quantity of water available for the firefighters, the hose stream. And that is the number that you see there for light hazard, 250 GPM. So the total quantity of water required for a light hazard occupancy for fire protection purposes is 300 plus 250 or 550 gallons per minute. So for what duration of time do you need to have this water, this flow rate available? Well, for the light hazard, it's 60 minutes. Now, these obviously are numbers that have been developed over decades, really, and shown in practice to be reasonable. So the 350, pardon me, 550 gallons per minute needs to be available for 60 minutes. And so that's 33,000 gallons of water that needs to be available for fire protection purposes for your building. For an extra hazard group 2, the for the sprinkler system, the design area again is 3,000 square feet times 0.4 GPM per square foot. That's 1,200 gallons per minute for the automatic sprinkler system, and 750 is required for the firefighter's hose stream. So that's a total of 1950 gallons per minute, and that is required to be in this system for 120 minutes. And so that means a quantity of 4,000 gallons of water must be available for the combination of the sprinkler system and the hose stream. Again, this is a table that has been developed just from experience and has been applied for decades and has been demonstrated to work. So this is the an approach to determining the quantity of water required for fire protection purposes for your building. If you don't have this quantity of water available, and for example, either you or maybe your water utility will do this calculation, and they may have a slightly different methodology that they use. But if they determine that their water supply system cannot supply this quantity of water to your building in the event of a fire, then you have to store water on site at your building. Then for the simpler unsprinklered buildings, typically smaller buildings, the methodology is a little different. Again, this is a core NAVFAC federal methodology, and again, don't get hung up on that governmental or military or anything like that. But with the unsprinkled, kind of the smaller buildings, the factors that are taken into account are what you see here: the occupancy classification, response time by the fire department. How long is it going to take the firefighters to get to your building? The type of construction: wood, concrete, steel, number of stories, separation distances between your building and nearby buildings, the floor area, and the firefighting access. And a simple but workable point system is used. So your building, the response time by the fire department, if the fire station is less than 2 miles away, your building gets 2 points in this system. If it's more than 2 miles, your building gets 3 points. The type of construction, and of course, this varies every time they rewrite the codes, but essentially ranging from the most fire resistive type of construction like concrete up to the least fire resistive type of construction, wood stud. And depending upon the type of construction of your building gets 1 to 5 points. Number of stories, if it's a 1-story building, your building gets 1 point. If it's 2 or more stories, your building gets 2 points. And that's the end of the, no pun intended, that's the end of the story. The experience has just shown that there's no reason to consider that a 30-story building warrants more points in this system than a 2-story building. So the number of stories in your building, single story, 1 point, 2 or more stories, 2 points. Building floor areas, 7,500 square feet or less, 1 point, up to 40,000 or greater, 5 points. And these are the numbers that have been arrived at just simply by experience over the years. The separation distances between your building and nearby buildings more than 60 feet, 1 point, 21 to 59 feet, 2 points, less than 20 feet, 4 points. Maximum hose layout, that's from the hydrant in the street to the pumper truck to the connection to the fire riser in the stairwell. 180 feet or less, 1 point, 181 to 230, 2 points, more than 230 feet, 4 points. So your building is awarded points on these scales. And then, so your building now has accumulated a certain number of points. And then in this system, you go to this table here, which experience has shown is a satisfactory estimate of water demand for an unsprinklered building, no fire sprinkler system. The occupancy hazard classifications, light hazard up to the most hazardous. And if your building, as an example, light hazard, gets 6 to 10 points, the fire flow requirement for fire protection purposes is 750 GPM. And if your building light hazard occupancy has greater than 16 points, then the requirement for fire protection purposes 1500 GPM. And then on up to the most hazardous extra hazard classification, 6 to 10 points, 2500 GPM, greater than 16 points, 5,000 GPM, gallons per minute. And for what number of minutes is this flow required? Light hazard, 6 to 10 points, 60 minutes, greater than 16 points, 120 minutes, on up to, for the extra hazard building, 6 to 10 points, 150 GPM, pardon me, 150 minutes. And then greater than 16 points, 240 minutes. So this is a methodology for determining the quantity of water needed for fire protection purposes for your building using this federal approach, which has been on many buildings over many decades to be reasonable. fairly simple way to do it. And here, just for illustration purposes, we've been talking about the water required for fire protection for buildings, but there are these other situations that you can encounter where fire protection is an issue. Like an example is fuel farms, petroleum oil, lubricant, flammable fluids. And this is a federal methodology for estimating the water requirement for fuel farms. And it's based on the diameters of the tanks. A up to 64-inch diameter fuel storage tank, the fire flow rate required is 500 GPM. On up to tanks 200 inches or more in diameter, the fire flow rate requirement is 1,500 gallons per minute. And for all of these, the minimum duration of time for which these flow rates must be available is 240 minutes. Now you might, in looking at this, say, well, why is this water requirement only based on the diameter of the tank and does not take into account the height of the storage tank? Well, the reason there is that in the event of a fire in a fuel tank like this, the only fuel that is burning is that which is right on top. And the depth of the fuel is not considered because it's not burning. The fire burns at the top, and that's so the diameter is the only thing that is relevant. And here again, this is the federal or NAFAC approach for pressurized tanks of certain sizes and the flow rates required. Okay, now the water supply pressure requirement. Where this in the law, in many instances in building design, where this comes into play is the pressure requirement in an automatic sprinkler system, water sprinkler system in a building. And typically you go to a catalog and pick out your the sprinkler head that you're going to use. And typically it will say, the manufacturer will say, well, if you provide water at a pressure of at least 20 PSI at this head, it will distribute so many GPM per square foot over such and such an area, 200, 300 square feet, something like that. So you need, with a water sprinkler system, you need to have enough pressure at the head. And so you calculate the pressure requirement and size your piping for the most hydraulically remote location in the building. That sprinkler head that is furthest from the point where the water enters the building. So if you're getting the water from your municipal utility, and if they tell you that we can deliver water to your building at 50 PSI.
Oh, Paul, your mic is out.
Okay, not quite sure why things I'm having a little, okay, I guess I'm okay. Well, I've
Yeah.
lost the Zoom control panel.
Just share the screen.
Uh,
Share the slides again. You're back on.
okay, well, let's see. I think I'm going to have to leave the meeting because I've lost the Zoom control panel.
No, you're in. You're there.
Okay, so you can see my screen.
Yeah, we just shared your slides.
Okay, stick with me. But I can't, I don't have a control panel. Well, if you can hear me and if you can see my slides, I'll press on. But for some reason, I lost the Zoom control panel. Okay, so the the water.
Oh, Paul,
Yeah.
I sent you the invite again from your email. You can join again if you want.
Okay.
You have to leave this one.
Okay. All right. Let me do that. Stick with me here. I'm okay. Click here to join. So now I'm rejoining, and
Well, you're here now, so
this
all what
is
you need is share the screen. There, share the slides. Down, mouse down, you'll see share screen, and you can share from there. Mouse over, let your mouse way down your screen, and thumbs up. Either lower screen or up, you will see the buttons will appear. All the controls will show up.
okay. Jiminy Christmas. This is really weird.
Can you find the controls?
No, that's the point. I can't.
Well, you have mouse with your mouse, go way down on the screen or way up. The controls will show up. Depends on your systems. But mine is way down. When I mouse down, the controls will show up.
Oh, okay. Share screen. Okay, now
now you will get onto your, there you go.
okay. All right. And yeah, okay. Now I finally have the Zoom control panel. slideshow from the current slide. Okay, we should be okay now. You
That's all good.
use my slide, and I'm going to let's move now to fire extinguishing systems. The what I didn't have a chance to show you was the sizing of the pipe in the sprinkler system. You've got 30 psi you can lose between where the water enters the building and that most remote sprinkler head, and you basically you just make a preliminary layout of your piping system, 1.5-inch pipe from here to here, 1 inch from there to there, 3/4 from here to there, and then a half inch at the end, and use the typical hydraulic head loss tables like you have in the plumbing code to calculate the loss for that, the head loss for that initial trial and error layout. And if it turns out that you're losing more than 30 psi between the start and the finish line, you need to increase the pipe size somewhere from 1.5 to 2 inch or whatever. So we don't have enough time to go into that. Let's now take a quick look at fire extinguishing. Excuse me, fire extinguishing systems. The one that we have been talking about and that is most common is the automatic water sprinkler system. There are others. There is our what are called foam or A3F, aqueous film forming foam systems. These are a sprinkler system that mixes the water with a chemical before it discharges into the space. And the water comes out in a foam, a bubble foam, and this is used in a situation where you have like liquid fuel fires, like gasoline or jet fuel, things like this. And this foam floats on top of the fuel that would be burning, and it smothers the fire. And so this kind of a system, which is quite sophisticated, is typically used in a place like an aircraft hangar or maybe in a vehicle garage. And it's because the big threat is fuel fires, and you can't put those out with water. The standpipe, again, that's typically the vertical pipe running up the stairwells, and that is pressurized, and the fire at each floor on the multi-story building, there is a connection where the firefighters connect to that, and they then have pressurized water to fight the fire with. Dry chemical systems, again, typically used where water is not effective. This place where they're used a lot is in kitchens, because grease fires are a threat there, and the particularly the exhaust system, like in a kitchen, it accumulates a lot of grease. Because you're using open flame for cooking, there's a risk that you can get a fire started in the ductwork for the exhaust system. And in the event a fire is sensed, it automatically releases a dry chemical that smothers the fire. Carbon dioxide systems, they are quite effective at putting out fires, but they can only be used in locations that are not normally occupied by people, for the reason that if you flood an occupied space with carbon dioxide, the people can't breathe. And so there's a hazard to life. So carbon dioxide systems are typically used in unoccupied spaces like transformer vaults, things like that. The item 6 there, Halon 1301 and clean agent systems, these were developed a few decades ago, 2 or 3 decades ago, to deal with the proliferation of spaces in buildings with a lot of high value electronic and communication equipment in them. And a recognition of the fact that if you had a fire break out in a wastebasket, you didn't want the uh, water sprinkler system to automatically actuate and ruin your electronic equipment and lose all your data and those sort of things. So Halon 1301 was a proprietary gas system that could be released into the space. It would reduce the oxygen level to a point where the fire could not burn, but there was still enough oxygen remaining in the space that it would allow the people enough time to get out of the space, and it would not damage the electronic equipment. This Halon 1301 product was, as time went on, identified as an environmental hazard and has been pretty much banned and taken off the market now, but it's been replaced by some comparable gas systems that are lumped together and called clean agent systems. Okay, let's see. We've just got a couple of minutes left. Oh, okay. Let's. This is the calculation of the head loss in the piping system for an automatic sprinkler system. And the approach you take is you you lay out your piping system, various size pipes for various lengths between where the water enters the building and that last sprinkler head. And you convert the all of the fittings, the elbows, T's, valves, etc., to equivalent lengths of straight pipe. And so the head loss is calculated on the basis of that equivalent, those equivalent lengths of straight pipe. And then you just use this fairly familiar figure here, commonly found in the plumbing code, that allows you to calculate the head loss at different flow rates for different size pipes. So you've got the flow rate in GPM on the horizontal axis, the pressure drop for the different sizes of pipes that you see there. And you just use a simple little figure like this to calculate the pressure drop between where the water enters the building and that most remote sprinkler head. Okay, oh, this is a picture of a typical takeoff at a floor in a multi-story building. The fire riser rising vertically in the stairwell. There you see an indicator type shut-off valve, an indicator type. Typically it either has a little sign on it that says open closed, or it has a rising stem so that you can, a maintenance person or anybody can quickly glance at it and see that that valve is open. Because if that valve is not open, then the entire floor is at risk because it won't have any water for the sprinkler system or for the firefighters. check valve to prevent backflow. The water flow switch there, that's the kind of the key sensor of whether or not water is flowing in the pipe. If water is flowing, that means one or more of the sprinklers on that floor have opened and are discharging, and therefore putting two and two together, that means there's a fire on that floor. And that's what sends the signal to the alarm panel down on the first floor, the firefighter panel, and it sends a signal to the firehouse saying there's a fire in this building. And okay, that kind of gets us out of time here. So I'm going to speed through the rest of these slides and bring things to a close because we're out of time. And here I'm flipping through these slides very, very quickly for the simply to show you, to illustrate for you the quantity of codes that are involved in the regulation of fire protection. And then these are some quiz questions. That gets us to the end of our time. And so I hope that this was about what you thought you were signing up for, that it gives you a fast picture of fire protection in buildings and will allow you to move forward with the your building design projects as they come across your desk. With that, again, thank you very much for letting me chat with you. And I'm now going to just close things out and wish you all to have a nice rest of the day. Thanks.